All right, today we're cracking open the Data Detectives Toolkit. We're going to look at some seriously powerful tools for solving those tricky puzzles hidden in your data, especially when that data gets a little bit messy. So let's just dive right in.
So you've got data, right? But what happens when it doesn't play nice? It doesn't fit that perfect, clean bell curve they taught you about. Maybe it's all skewed to one side, or it has some crazy outliers. Heck, maybe it's not even numbers at all, but ranks, like strongly disagree to strongly agree. This is a super common problem, and it's exactly where our detective work kicks off. Because your standard tools, well, they can totally fail you here.
The easiest way to think about this is that statistics kind of come in two flavors. You've got your parametric methods, which are like a really strict baking recipe. You need the exact right ingredients and conditions, like that perfect bell curve, or the whole thing just collapses. But then you have non-parametric methods, and these are like a freestyle cook. They're super flexible, they work with pretty much anything you throw at them, and that makes them so powerful for the kind of messy data you find in the real world. So what's the secret sauce for this freestyle cooking? It's actually pretty clever. Instead of getting hung up on the exact values in your data, these methods often just look at the ranks. Which one's first, which one's second, third, and so on. And that simple little trick is what makes them distribution-free. It makes them super resistant to those weird outliers that would totally mess up a stricter recipe. It really is a data detective's secret weapon. All right, let's grab our first gadget from the toolkit. This is the chi-square test, and it's your go-to tool for answering a really simple but important question. Are these two things secretly related? To see how it works, we're going to open up our first case file, the airline ticket mystery. Okay, here's the evidence laid out on the table. We're looking at the number of people who bought different kinds of airline tickets for either a domestic or an international trip. Now, just looking at it, it might seem kind of random, right? But the big question we as data detectives have to answer is this. Is there a real, statistically significant connection here? Does the class of tickets someone buys have anything to do with the kind of trip they're taking? So, in any good investigation, you have to start somewhere. You need a baseline assumption. In statistics, we call this the null hypothesis, and it's pretty simple. We just start by assuming there's nothing going on. We assume there's absolutely no connection. Ticket type and trip type, totally independent. Our whole job now is to see if the evidence is strong enough to blow that assumption out of the water. So we run the numbers through our chi-square gadget, and it spits out this value, 100.43. Now, what is that? That's our test statistic. And you can just think of it as a score that tells us how different our actual data is from what we would have expected to see if there was really no relationship at all. And here's the most important part. The bigger the score, the bigger the difference. And a score of over 100, that's massive. I like to call it a surprise score. Think about it. If these two things were really unrelated, getting data that looks like this would be a huge, incredible surprise. So a high score like this means our starting assumption that there's no connection is starting to look really shaky. Okay, but how big of a surprise are we talking about, really? That is where the p-value comes into play. The p-value is the final clue. It tells us the exact probability, the chance, that we would get a surprise score this big just by pure dumb luck, assuming our initial idea of no relationship was actually true. And this leads us to a super simple but incredibly powerful rule of thumb. It's kind of the golden rule of a lot of statistics. We set a line in the sand, usually at 0.05 or a 5% chance. And the rule is, if our p-value, that chance of it all being a random fluke, is less than 5%, we say, nope, not a fluke, and we get to reject our initial assumption. So back to our airline mystery. With a surprise score that high, our p-value is, well, it's practically zero. It's way below that 0.05 line in the sand. So we follow the golden rule. We confidently reject that no connection idea. The verdict is in. There absolutely is a statistically significant relationship between ticket type and trip type. Case closed. Okay, but wait. There's more. That same chi-square tool, it has another awesome setting. This one isn't about comparing two things to each other. It's about comparing your data to a specific theory, a pattern you think might be there. So let's open up case file number 2, the suspiciously perfect pattern. This is called the goodness of fit test, and it's super useful. The question and answers is really simple. Does my data actually fit the pattern I think it should? So for example, a manager might guess that customer complaints are spread out pretty evenly across all 5 weekdays, right? That's the pattern. So the starting assumption, the null hypothesis, is that the data does fit that pattern. And here's the best part. The method is exactly the same as what we just did. It calculates the same kind of surprise score to see how much your data deviates from that perfect pattern, and you use the exact same p-value golden rule to make the final call. Easy. Okay, time to grab the last tool from our kit for today. This is the Wilcoxon signed rank test. And this is the perfect gadget for any before and after situation. It's built to answer one question. Did that thing we did actually make a difference? Time for our final case, the post-campaign heist.
Now, this might sound a little complex at first, but I promise the idea behind it is beautifully simple. Let's say you've got employee performance scores from before and after some new training program. Step 1, for every single person, you just calculate the difference. Just subtract the before score from the after score. Step 2, you rank those differences based on how big they are. Don't worry about whether they're positive or negative for now. Just rank the size of the change. And finally, step 3, you do a little math that boils all of that down to a single, powerful number, a z-score. Okay, so let's imagine we run our test on that training program, and we get a z-score of -2.50. Just like with chi-square, this is our final summary score. Now, that negative sign tells us something about the direction of the change. But for now, what we really care about, the thing that tells us if it's significant, is just the size of that number. And guess what? Just like we had a golden rule for the p-value, we've got a super simple one for the z-score too. For most tests, if the absolute value of your z-score, which is just a fancy way of saying ignore the minus sign, is bigger than 1.96, then your result is statistically significant. It's honestly that straightforward. So let's apply the rule to our number. The absolute value of -2.50 is just 2.50. And is 2.50 bigger than 1.96? You bet it is. So we've got our verdict. We can say with confidence that the training program made a significant difference. Bam! Another case closed. All right, let's take a quick step back and just look at what we've accomplished. We've just added a whole new set of seriously powerful gadgets to our Data Detective Toolkit. These are the tools that let you dive into that messy, real-world data and actually find the hidden truth. So really, it all just boils down to knowing which tool to grab for which job, right? If your question is, are these two things related, like our airline tickets, you grab the chi-square independence test. If your question is, does my data match this specific pattern, well, that's the chi-square goodness of fit test. And for any of those classic before and after questions, the Wilcoxon test is going to be your best friend. And that's our deep dive for today. We've seen how these incredibly flexible and powerful non-parametric tools really do act like a detective's magnifying glass, letting you see connections and patterns that would otherwise just stay hidden in the noise. So the real question I want to leave you with is, what hidden stories could these tools uncover in your data?